day everyone, I'm Maliana Masanit and I will discuss to you the intensity in interference pattern. So first, let us discuss what is interference. In physics, interference is a phenomenon in which two coherent waves are combined by adding their intensities or displacements with due consideration for their phases difference. The resultant wave may have greater intensity or lower amplitude if the two waves are in phase or out of phase respectively. So in intensity of interference pattern, let's consider the E fields or the electric fields coming from the double slits. The E field from S2 has a phase lag pi due to the extra path difference of R2 and R1. Next is intensity of interference pattern in phasor representation of electric field. First, what is a phasor? A phasor is a complex of number representation that encapsulates both magnitude and phase of a sinusoidal function. It is usually represented in the form of rotating vector or a point in the complex plane. The term phasor is a blend of two words, phase vector. So in here, E field is a vector or phasor rotating in the x and y plane with an angular frequency. The time variation of this electric field is given as the horizontal projection, the light blue color of the phasor, and the electric field dark blue color. Phasor representation is an essential concept in the field of electrical engineering, especially used in the analysis of alternating current circuits. It is a mathematical method that simplifies the study of these circuits by converting differential equation into simple algebraic equation. In the context of oscillating electric field in the x and y plane with an angular frequency, you can represent it as a phasor. Let's assume the electric field is given by electric field as a vector phasor rotating in the x and y plane with an angular frequency. So the time variation of this electric field is given as the horizontal projection, the light red of the phasor and the dark red. If the electric field is rotating in the x and y plane, the angle phi will be changing with time. The rotation of the phasor corresponds to the oscillation of the electric field in the x and y plane. To express the time dependence, you can use Euler's formula. This allows you to work with complex numbers and phasors. Let's recall that there are two coherent electric fields with a slight phase difference coming from the double slit. The E field from S2 has a phase lag phi due to the extra path difference R2 and R1. Next is the phase difference relates to path difference. Here we have the lighter cyan wave slightly ahead of the blue wave. The R2 and the R1 are called the path difference measured in length. Phi stands for the phase difference measured in radians, and the wavelength sign it is a complete cycle measured in wavelength, and the 2 pi it is a complete cycle measured in phase. This given the relation of phi is equals to 2 pi over wavelength times the phase difference measured in length and equals to k times the path difference measured in length, where k is equals to the a complete cycle measured in wavelength divided by a complete cycle measured in phase. So this the k is also called as the wave number.
For the continuation on intensity of interference patterns, at a given point on the screen far away from the two slits, the total E field or electric field at point P is given with the vector sum of the two phasors, E sub 1 and E sub 2. To find the magnitude of the resultant phasor, we use the law of cosines. E squared sub P is equal to E squared plus E squared minus 2E squared cosine times the pi minus the phase difference. Using the symmetry of the cosine function, Cosine times pi minus phase difference is equal to the negative cosine times phase difference. We have e squared sub p is equal to e squared plus e squared minus 2e squared cosine times pi minus a phase difference equals to 2e squared plus 2e squared cosine times phase difference equals to 2e squared times 1 plus cosine times phase difference. Using another trig identity, 1 plus cosine times phi, or the phase difference, is equal to the 2 cosine squared times phase difference over 2. We have e squared sub p equals to 4e squared cosine squared times the phase difference over 2. And this gives the equation of the resultant electric field at point P equals to the 2e cosine times the phase difference over 2. The intensity of an electromagnetic wave is given by the average magnitude of the Poynting vector. When you say Poynting vector, it describes the energy flow associated with an electromagnetic wave. In this stands by the capital S with the subscript AV. So in general, the Poynting vector is proportional to the square of the magnitude of the electric field. So for the intensity at point P, calling the maximum intensity when phase difference is equals to 0 or the maximum intensity, we can write this expression as resultant intensity is equals to the maximum intensity cosine squared times the phase difference over 2. Note that when the two waves are in phase 0 or straight ahead, the resultant intensity is at maximum, and when the two waves are exactly half cycle out of phase, or pi is equal to pi, the resultant intensity is identically 0. Although the waves are in phase at the slits, their phase difference at P depends on the path difference. In the equation, path difference is equal to the R2 minus R1, or ray 2 minus ray 1 is equals to the d sine theta. A path difference of wavelength for constructive interference corresponds to a phase difference of 2 pi radian. A path difference is the same fraction of wavelength as the phase difference is over 2 pi. Recall from our geometry, we have the following picture for the path difference, where theta denotes as the angular position of the observation point P, and in the equation r sub 2 minus the r sub 1 is equal to the d sine theta. Substituting this into our previous equation, we have the phase difference, or phi, equals to the 2 pi over the wavelength times the r sub 2 minus the r sub 1 equals to the 2 pi distance, or 2 pi d over the wavelength times sine theta, or the angular position. Note that we expressed one full cycle as 2 pi so that the phase difference has to be in radian. Putting this expression for the phase difference into our previous intensity equation for our two-slit interference pattern, we have resultant intensity is equal to the intensity maximum cosine squared times the phase difference over 2 equals to the intensity maximum cosine squared times 1/2 times the 2 pi times d over the wavelength sine theta, which gives the final equation. The resultant intensity is equal to the maximum intensity cosine squared times the pi times d over the wavelength sine theta, where the symbol phi denotes as the phase difference between the two waves at each point in the pattern, while the d sine theta denotes as the path difference from the two slits at each point in the pattern.
Good afternoon, everyone. Today I will discuss the continuation of Ms. Okias. In the context of the two-slit interference in physics, intensity refers to the brightness or energy per unit of area and the resulting interference pattern on a screen. It is also determined by the superposition of waves from two slits, leading to the regions of constructive and destructive interference. The higher intensity The higher intensity corresponds to brighter regions where constructive interference occurs. Then, while lower intensity corresponds to the darker regions with destructive interference. Interference in thin films in physics refers to the phenomenon where light waves reflecting off the upper and lower surfaces of a thin film interfere with each other. This interference can result in a spectrum of colors due to the variations in the path of the length traveled by the waves. Thin film interference is also commonly observed in soup bubbles, oil slicks, and coatings on surfaces. The colors produced are result of the constructive and destructive interference. It depends also on the phase of relationship between the reflected waves. Also in physics, phase shifts during reflection refer to a change in the phase of the wave when it reflects off a surface. So the phase of a wave also corresponds to its position in the cycle of oscillation. So when a wave reflects off a medium with a different refractive index, also the phase of the reflected wave can shift. So if the reflecting medium is denser, or when we say denser, it is higher refractive index, so there is a typically phase shift of 180 degrees or a half of a wavelength. So this phase shift is important in understanding interference. Standing interference phenomena such as those observed in thin film interference or when waves interact with multiple surfaces. So interference from a thin air gap in physics refers to the phenomenon where light waves experience interference as they pass through a narrow or a space filled with air. So this is often encountered in the context of the thin films where there is a small gap between two transparent layers. So the waves undergo reflection from those both surfaces of the gap. It also lead to interference effects. So the resulting interference is being patterned can produce colorful fringes or the bands, and the specific colors depend on the thickness of the air gap and the wavelength of light. So this phenomenon is similar to thin film interference and is a consequence of the superposition of the waves. So in physics, interference is a phenomenon that occurs when two or more waves overlap. Also, it results from the combination of these waves leading to a redistribution of their amplitudes. Interference can be either constructive, where the waves reinforce each other and produce a larger amplitude, or destructive, where the waves also partially or completely cancel each other out. So it results in a smaller or zero amplitude. So this phenomenon is observed in the various wave systems, including electromagnetic waves such as light and the acoustic waves. Interference plays a crucial role in the phenomena like the colorful patterns in soup, bubbles, diffraction, gratings, and the interference fringes in double slit experiments.
Interference from a thin air gap. Solving for only positive, we have 2t is equals to lambda over 2, 3 lambda over 2, 5 lambda over 2. Rewriting the equation where 2t is equals to m plus 1 half times lambda, where m is equals to 1, 0, 1, and 2. Destructive wave number 1 and 2 upon reflection must have a net phase difference of m plus 1 half times 2 pi, where m is equals to 0, 1, and 2. Rearranging the equation. Finally, we have 2t is equals to m lambda, where m is equals to 0, 1, and 2. Now let's proceed to thin and thick films. Example A, light reflecting from a thin film, while example B, light reflecting from a thick film. In a thin film, the waves reflected from the two surfaces is part of the same burst and are coherent, and the interference effects can be observed, while in thick film, the waves reflected from the two surfaces are from different bursts and are not coherent, and interference effects are difficult to observe. Another thin film example, non-refractive coating on lens. Wave number 1 reflected from top interface of the coating, where N coating is greater than N air is equals to 180 degrees phase shift. While in wave number 2, reflected from bottom interference of coating, where N glass is greater than N coating is equals to 180 degrees phase shift. Now, an interference from a thin film. Since both wave number 1 and number 2 suffers the same phase shift upon reflection, the net phase difference will be from the path difference to t only. So we have the standard condition, net phase difference due to path difference only. There is one more consideration. The path difference is accumulated in medium with N coating so that the relevant wavelength should be lambda N is equals to lambda divided by N coating. Now, in constructive, the formula is 2t is equals to m lambda N is greater than m is equals to 0, 1, and 2, and 2n coating t is equals to m lambda, m is equals to 0, 1, and 2. In destructive, 2t is equals to m plus 1 half times lambda, where m is equals to 0, 1, and 2. 2n coating t is equals to m plus 1 half times lambda, where m is equals to 0, 1, and 2. Note, in addition to wavelength modification, the RHS dependence are switched with respect to the air gap case.
Interference in thin films occurs due to the reflection of light waves at different interferences within the film. The varying path lengths of these reflected waves cause destructive or constructive interference, leading to the observed colors or changes in light intensity. What specifically are interference happens when two or more waves align in such a way that their peaks or troughs coincide, resulting in an amplification of the wave's intensity. In the context of thin films, constructive interference occurs when the reflected waves from different interfaces meet and reinforce each other, leading to brighter colors or increased light intensity at certain wavelengths. Destructive interference arises when two or more waves align in a way that their peaks coincide with the troughs of others, causing the reduction or cancellation in the overall wave's intensity. In thin films, this occurs when reflected waves from different interfaces meet and interfere, resulting in diminished or even no light at specific wavelengths, leading to dark or faded colors. The formula for constructive interference in thin films, especially for a specific wavelength, lambda of light, is given by 2n c dot, or d equals m divided by c dot divided lambda, where n is the refractive index of the film material, which d is the thickness of the film, m is an integer representing the order of the interference 0, 1, 2. The formula for the constructive interference in thin films is similar to that constructive interference. For destructive interference at a specific wavelength, lambda, the formula is 2n divided by c dot, d equals m plus 0.5 c dot lambda, where n is the refractive index of the film material, d is the thickness of the film, m is an integer representing the order of the interference 0, 1, 2, 3. Newton rings refer to a series of concentric, alternating bright and dark rings observed when a plano-convex lens is placed on a flat glass surface. This phenomenon occurs due to the interference of light waves reflected from the top and bottom surfaces of the air film formed between the lens and the glass surface. The varying thickness of the air film causes constructive and destructive interference, leading to the observed ring pattern. This effect is used in all optical measurement and to determine the flatness of surfaces in various scientific applications. The Michelson interferometer is an optical instrument used to measure small differences in the wavelength of light and for precise measurement of distances. It consists of a beam splitter that divides a single light beam into two perpendicular paths. Mirrors at the ends of these paths reflect the beams back toward the beam splitter, where the recombined when the recombined beams meet, interference occurs, producing an interference pattern that can be used for various measurements such as determining the refractive index of materials, studying thin films, or detecting small changes in distance by observing changes in the interference pattern as the distance is altered. This instrument played a pivotal role in numerous scientific experiments, including the Michelson-Morley experiment that aimed to detect the Earth's motion through ether, ultimately leading to the development of the theory of relativity. The Michelson interferometer was invented by the American physicist Albert A. Michelson in the late 19th century. Around 1881. Michelson is well known for his groundbreaking work in optics and for being the first American to receive the Nobel Prize in Physics in 1907 for his precision optical instrument and of optical principles. He helped establish his invention of interferometer, revolutionized various fields, particularly in the realm of measurements involving light waves and their properties.